Hello everyone, I am Nirav Bhatt. Today's class is going to about genome assembly. Before we go and understand what is genome assembly, let's discuss why we want to study genome assembly. I'm sure that in earlier class we discussed about importance of genome and its implication in the healthcare as well as other industries. The cost of genomics sequence in 2003, when we first time did human genome sequencing, was a $3 billion. Couple of years ago, 2018, thanks to next generation sequencing, the cost of sequencing is $1,000. And there are companies who are planning to reduce the cost of genome sequencing to $100 in near future. Hence, we will have a lot of data that will come at our hand for genome assembly. And why it is an important problem? Because next generation sequencing help us to sequence DNA, RNA in a quick and cost-effective manner. However, we have a large genome and it cannot be read from starting to end in a one go, or what I call it in a linear fashion. Hence, what we have to do is we have to take a DNA, fragment it, and then fragments, which are called reads in the field, are sequenced individually. Now, we have a set of sequenced fragments or reads, and the objective of the genome assembly problem is to sequence reads to convert into a genome. And why it's challenging? Let's discuss about it. So already in earlier class we discussed about shotgun sequencing and sequencing whole genome approach you have studied, where we have a multiple copies of genome. As I told you, we'll actually fragment it and have a set of reads, and this all set of reads are sequenced and gets us a sequence reads. So here, for example, in this particular green reads is sequenced as A, G, T, A, C, C, A, T, A, G. Similarly, other reads have been sequenced at other format. But if you look at very carefully, there is certain part of this sequence read is overlapping with another sequence read. And similarly, if you look at this part of this sequence read is overlapped with some part of this read. So what we have is overlapped read or sequence reads. Can we utilize this information? So the whole idea is take a read or sequence reads, use assembly algorithms to actually create an assembled genome using this set of reads available to us. It looks straightforward. Then why is the genome assembly problem challenging? Let's go to the simple question or simple problems. Let's take a simple sentence in English, and I will call this problem a sentence decomposition problem, where we want to take a sentence and convert into words. For example, here I am having a sentence, I am studying genome assembly. Then I will perform a decomposition operation which decompose this sentence based on certain dictionary. Of course, we all know those dictionaries, and create a set of small fragments or words which are here. Assembly, I am studying genome, and I. It's a straightforward process if I have a dictionary. In other words, I know each element in my sentence. For example, words. Correct? Otherwise, someone who doesn't have a dictionary can actually make I am as a word. It's possible. However, we have been taught that if there is a space, there are two different words. So I and am are two different words we recognize based on our learning of space. Now sentence decomposition is a very straightforward under the assumption that we have a dictionary. However, let's ask me a little more complex problem, string reconstruction problem or sentence reconstruction problem. If I give you set of this string or words, I want to reconstruct a sentence. We have studied in English, this sentence makes sense. However, one who did not study English, for them this is possible sentence, genome assembly studying IM, or genome I assembly, genome M assembly studying I, etc. So we can construct several sentences, of course in this case are finite sentences, from this set of strings. Of course, it is always easier to break down than reconstruct them. Here, one of the reasons we cannot reconstruct in a straightforward manner because we have multiple options and we do not know which option is correct. Or indeed a sentence which has been used to get these words. Same way, in genome assembly problem, we have a set of reads. On top of that, we have actually set of repeat reads. In other words, think of the sentence I give you, speak same sentences couple of times, I record it, and for each time I actually decompose into the words, but I do randomly instead of having a dictionary. In that case, what I will have is some overlapping regions where IM can be one sentence in one place, while in other place I and M are two different words. So how we can actually take this overlapping reads where we do not have a complete genome, take it from this overlapping read, create a more common consensus of genome sequence, and finally assemble complete genome. And we'll realize in a couple of more slides that it is easier to sequence or generate reads than to assemble them. Why? We'll see later on. And then what is the genome assembly problem? Given a very large number of overlapping reads, find a smallest, that is also a question mark, whether it's smallest or not, but what we are interested in finding a sequence that contains all of them or all of those reads which we have sequenced in an ideal scenario. And finally, we want to do is we have to come up with an algorithm which actually takes these reads and provides us an assembled genome. And that is what is a genome assembly problem. Before I go to the genome assembly problem, let me do following. Let me define certain concept. So we'll start with the concept of k-mers. So let me define what is a k-mer and k-mers. So here a k-mer is a string of length k. Okay, and the k-mers is a set of all possible substrings of length k that are contained in a given string. Why we are interested in k-mer? Because they are equivalent to a word in a genome assembly problem. And what we want to do is we want to actually get k-mers from the sequence. So let's start with this particular sequence TATGGG So if I am interested in finding k-mers of length 1, which where k is equal to 1, each k-mer, this is a set where TATGGGTGC. That's are the k-mers in this particular sequence. What are the two k-mers are TA, AT, TG, GG, 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 GT, TG, GC. Here, how did I got k is equal to 2? I have a overlapping TA AT, TG, GG, GG again, GG again, GT, TG and GC. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So I have constructed 9 tumors from this sequence. Similarly, I can do for k is equal to 3 and k is equal to 4. Now the question, which is very interesting question to ask, is what is the number of possible k-mers in a string of length n? That we will see in a while. So what is the number of possible k-mers in a given sequence or string of length n, which is n minus k plus 1. Let's go back to the previous slide and see if we can verify that. So here we have a k is equal to 1. The sequence length is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. N is equal to 10. Then number of k-mers or number of possible k-mers in a given string of length n is equal to n minus k plus 1, which is equal to 10. Let's see, we have 10 elements or not. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes, we have 10 elements. Similarly, for k is equal to 2 and n is equal to 10, we can compute n minus k plus 1 is equal to 10 minus 2 plus 1 is equal to 9. We have 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have a set of 9 2k-mers. Similarly, we can find for k is equal to 3, it should be 10 minus 3 plus 1 is equal to 8, and similarly for k is equal to 4, t minus 4 plus 1 is equal to 7, and you can count that we have here 1, 2, 3, 4, 5, 6 and 7 elements. So this is the interesting part about k-mers, that we have, if we know what is the sequence length, we know how many k-mers we get of different size. Typically, k-mers contains nucleotides. That's why we have either A, T, G or C in the sequence which we have discussed in the previous slide. Now, the one other question people can ask, what are all possible k-mers which are denoted as mk for a given k? Remember that this question is different from the string. What we are saying is that in each position, or what are possible combinations of all k-mers for a given k. So if I put a k is equal to 1, the answer is mk is equal to 4. In other words, I have only possible k-mers of size 1 are A, T, G and C. If I put k is equal to 2, the all possible combination are 16. How do we get that? Simple. We have to look at all possible combination. So it can be looked at as a diagram and we can construct. I will put some of them, like say AA, AT, AG, AC, similarly TA, TT, TG, TC, and we can henceforth do similarly for G and C. So we have already 8 and same will go for other 8. So we have a total 8 plus 8 plus 8 plus 8, 8 plus 8, 16 possible combination of k-mers. In other words, if you take any sequence and take a k is equal to 2, then the only possible k-mers are there are this many. Unique you can think of k-mers are there are 16. It can repeat, but you cannot have more than that. One of the reason we are learning k-mers is because it actually replaces the words in the sentence for the genome assembly problem. Other reason is we can actually ensure that we get a k-mer size of reads from some of the modern technologies. So we are getting a better at not only reducing the cost, but also providing a better and better reads or consistent reads so that the existing algorithm can be used to sequence the genome or assemble the genome. Now, so far we have talked about is a k-mer. Now let's go and see the problem we want to solve using these k-mers. So what I'm going to do is I'm going to project a genome assembly problem as a string reconstruction problem, and that I have showed you in earlier slides that they are equivalent. In other words, if I provide an algorithm for string reconstruction problem, indirectly I am providing algorithm for genome assembly problem, and the most of the example I will take are basically from the genome assembly problem. So what is the string reconstruction problem? It's a very simple problem. I have a set of k-mers and I want to reconstruct a string. I want a simple algorithm which provides me a string. We will not worry about uniqueness of the string or whether we have actually reconstructed original string or not. First we will worry about how to or address the problem of how to get a string from a set of overlapping k-mers. So I have taken a simple example to explain a naive algorithm. Here in example we have 5 3-mers. Of course when I say k-mers they are always overlapping, remember that, and you can see that AAT, ATG are overlapping but not in the same sequence. So I cannot just reconstruct a string out of it or sequence out of it. And the question, as I told you, is to find a string or sequence. So what we are going to do is, for this algorithm, we find a pair of k-mers if they overlap in k minus symbols. Okay, that's what we are going to do, and then stitch them together. Remember, this sequence here I have given is in some kind of alphabetical order, so I cannot just go and use that. It is just serendipity that the first element of k-mer and the second element of k-mers are overlapping. That may not be true, you can see for the third one. Okay. So what is step 1? Let's generate k minus mers by removing the last symbol in the each k-mer. So what we have done is, I have taken this k-mer and removed the last symbol. So that will end up with a A. Similarly for ATG, removing G we will get AT. For GTT, by removing T we get GT. TAA we remove the A and get TA. And TGT we remove T and get TG. So first step is done. We got all k minus 1 mers by removing the last symbol or later. Now what we have to determine where to start a sequence. So what is the next clue for us is, we have to find any of these k minus 1 mers which are not overlapping or ending with any k-mer here ending with that k-mer, because they are overlapping. So here if you look at AA is overlapping with TA, AT is overlapping with AT. So they are ending with here AT, GT is ending here, TGG ending with TG. If you look at TA, is nowhere you can find it is ending with TA, no more. TG again ATG is ending with TG. So only element here which is not ending is with a TA is a TA. Hence, TAA should be a starting string for reconstruction. Remember that there might be possible, there are multiple k-mers which are not ending at all. So you might have multiple options for the starting. But in this case, we have only one starting string, which is TA. Now, what we are going to do is, we are going to find the next string which is actually starting with AAT. And then again we will look at the another one which is starting with AT. Henceforth, so now what we have is TA, then I have actually used a last two element to see whether I can find the first two elements of any three mers which start from AAT in my set, which is A, which is AAT. Similarly, I have found another three mers which start with AT because my previous string was ending with AT, and then keep doing it until I got to used all the k-mer in my sets. So now once I have that, I can reconstruct the string? I can reconstruct the string by simple manner. I'll take these three and then I'll draw this staircase and I'll take the last element of each subsequent three mers. So my string will be TAA, TG, TT. And that is my reconstructed string, TAA, TG, TT. It looks very straightforward, correct? Let's see another example. So I have taken bigger example where I have 15 three mers, okay, and you can count them. And objective is to find a string, same as a previous example. What we are interested in, finding a pair of k-mers if they overlap in k- symbols. That's the same idea we are going to follow. Step 1, generate k-1 mers by removing the last symbols. I have done that for all of them. Remember, last symbol here is A, then it will become AA, here is AAG, so I am removing G, so it will be AA. Similarly for the next one and henceforth. Okay. So I'll start with this one and end with this one, and last one is TG by removing C. Once I have this, next step is to search for the mer where I can actually start my string with. And what I'm looking for is any k-mer or three mer whose starting is not two mers or first k-1 symbols are not ending with any other symbols. So if you search that, you will find out ATG is the one which is not ending anywhere. You find anywhere any three mers ending in AT? Let's check. No. Correct? So what we can do now, we can start with ATG as a starting string. So what I did is I used ATG, then I found TGC. When I came to GC, I found that there are two possibilities. One is GCC and GCG. So two options. I have a fork now. What I should do? Simple algorithm says choose one of them and start your journey or continue your journey. So I have selected one option and continue. So I continued with the GCG, then another one I have to add is CGC, then again it comes as a GCG and I have to add GCC, then I am adding CCG. Now when I go back to GC, I want to find a new mer which start with CG. So I have 3 mers which are start with CG. Yes, I have CGC. However, I have already used that mer earlier in a sequence which is CGC here. You see. Now the problem is I cannot use that particular 3 mers again. It means I am stuck. What I have to do? I have to go back and start again. So what I will go back where I have actually had an option to choose. So I took a one path and that path ended with a dead end. I cannot continue. So I am going back to that path where I actually am taking another path. So I have to go back to the step where I actually forked and choose another option for a k-mer starting with GC and keep continuing again and ensure that whenever I have options, I choose the appropriate option. If I have not chosen appropriate option, I will end up with the dead end. Again I have to choose and keep repeating it until I get to use all of these 15 strings only once and get a legal path from starting to the end. As I told you, continue until all k-mers are used in reconstructing the string. And then what the answer I get it is my reconstructed sequence. So here reconstructed sequence is ATG, CAA, 8GC, CTA, GCG, CCG. We are close to it, but not really indeed near to it. So what we have to recall is the following, that whenever there are multiple options, we have to go back and choose another option. The question is, we have a solution, but can we improve this approach?